Chapter 4 for Stat 210 covers discrete random variables. So in this chapter, we will learn how to recognize and understand discrete probability distributions, how to calculate and interpret expected values, how to find probabilities of events within discrete probability distributions. And this chapter really just allows us to gain a deeper grasp on probability distributions by looking at distributions that may seem a little bit more familiar to us. We will practice finding probabilities and applying our knowledge to real-world situations. So as we get started talking about discrete random variables and discrete distributions, we want to talk about what a random variable is. So a random variable describes the outcomes of a statistical experiment with words. The values of a random variable may vary with each repetition of an experiment. Remember, discrete means countable, so whole numbers and no decimal places. Our notation for a discrete random variable, a random variable is denoted by an uppercase letter such as capital X or capital Y. The value a random variable may assume is denoted by a lowercase letter such as a lowercase x or a lowercase y. Probability distribution functions, which we will abbreviate as PDF. A PDF for a discrete random variable has two characteristics. First one is that each probability is between 0 and 1, and the second one is the sum of the probabilities is equal to 1. And these are some things that should make you think about our rules about probability that we've learned in the past. So probability distributions for discrete random variables can easily be represented with a table. So this table here, we see that we have a capital X here, which means these are the random variables. These are the things that it can assume. Probability that it equals each of the different ones. So probability that a random variable equals -1 is equal to 0.75. Probability random variable equals 0 is 0.2. Probability random variable equals 4 is 0.05. And notice that these probabilities should add up to 1. Now, this above table could be perhaps a probability distribution for a gambling game where, say, you pay $1 to play, and then 20% of the time you win $1, 5% of the time you win $5, and then 75% of the time you're losing. What if I gave you another table, only I left out one of the probabilities? How could we find this missing probability? Well, we could find this missing probability by taking and adding up all the other values and subtracting those from 1, and we'd get 0.07. And this above table could maybe be the probability distribution for the number of questions missed on an exam. But notice that we did have a value missing, and to find that value, we took and we added all of the other values up, and then we subtracted that from 1. Next, we talk about expected values. Expected values we can abbreviate as E of X. This is the same thing as the mean, so we can use expected value and mean interchangeably, and you will see that on your homework a little bit. Now, we are able to calculate this by using the table. Create a third column with X times the probability of X, and then adding that column up, we would have the expected value. So what we're doing here is we would have actual numbers in here for the values that a random variable could assume. We would have probabilities listed in here. We take the value here times the value here, giving us this value. Then adding those up, we would get the expected value. So let's go ahead and practice that. Find the mean or the expected value of the following probability distribution. Now, in order to do this, we would have to go ahead and multiply x times p of x a whole bunch of times. So 1 times 0.13, 2 times 0.22, 3 times 0.16, and so on. Then once you have done all of those, you would add them together, and that would give you your mean or the expected value. So here the expected value would be 4.37. Now, before, whenever we talked about mean, we talked about standard deviation or the variance, and that's something that we are going to continue to pair with it and talk about. So standard deviation, to find the standard deviation, we again can use this table. First, we find the mean, then we make a new column for x squared times p of x. Now this is really just x times p of x. And we've already made a column for x times p of x, so we'll just take that column times x again. So you're taking, we've already made this third column here when we found our expected value. So what we're doing is we're taking the first column times this column that we made, and that gives us everything in there. Now, to find standard deviation, then we will use this formula. The standard deviation is equal to the square root of the sum of the x squared times p of x's minus the mean squared. So you have to have found your mean first, because we do need the mean in the standard deviation formula. But this allows us to do this in a fairly efficient way using the table. Now, if you were asked for variance, we just wouldn't have to take the square root, because variance is standard deviation squared. So sigma squared, variance, is equal to the summation of x squared times p of x minus the mean squared. So let's go ahead and practice this. We went ahead and found our mean already. So let's go ahead and find the standard deviation here. So finding standard deviation, you're doing x times p of x, 2 times 0.22, and so on. Add that all up, we get 24.23. So we plug it into our formula. So 24.23 minus the mean 4.37 squared. You're going to follow order of operations. So you're going to, square things first, then you'll do your subtraction, and then we have that square root that we have to take care of. So we'd have the square root of 5.1331, giving us approximately 2.27. Now, there are a few special discrete distributions that we do want to make sure that we spend some time talking about. What you're going to notice after this chapter, we're going to get into continuous distributions, and we're going to see that there's going to be a name and some special formula we're going to follow for the distribution. So here with our discrete distributions, we have our way of dealing with it in general, and there doesn't necessarily have to be a formula for how we find the probabilities. But there are a few special discrete distributions where we have a formula that helps us find the probability based on some inputs from our scenario. As we move into continuous distributions in the next chapter, we're going to start to see that it's always going to follow some sort of formula. And so these special discrete distributions, this chapter kind of get us ready for that. So there's numerous special discrete distributions that have names and formulas that they follow. We're going to focus on two of them together this chapter. So we're going to focus on the binomial distribution and the Poisson distribution. So the binomial distribution, there are 4 characteristics that set apart a binomial distribution, and that's because it has to fit a binomial experiment for it to be a binomial distribution. So a binomial experiment has the 4 characteristics. First, of which is there must be a fixed number of trials. Another characteristic is that each trial can have only two outcomes, or outcomes that boil down to two outcomes, and these outcomes can be considered either success or failure. The outcomes of each trial must be independent. So what that means is that the outcome of your first trial cannot impact whether or not you're going to get a success or a failure on your second trial. And then the fourth thing is the probability of success must remain the same for each trial. So these are the four characteristics that a binomial distribution must have. A few things that we want to keep in mind as we're looking at binomial distributions. N is going to stand for the number of trials. P is going to stand for a probability of success. Q will stand for the probability of failure. And Q should be equal to 1 minus P. So some formulas for the binomial distribution. The probability that x equals little x is equal to n factorial divided by n minus x factorial times x factorial. That fraction times p raised to the x times q raised to the n minus x. This probably looks familiar a little bit. This first part here is simply a combination, which we saw in a previous chapter. The rest of this should kind of make sense as well. We're saying probability of success times the number of times itself for the number of times that we succeeded. So if we succeeded twice, we're squaring it. And then the probability of failure raised to the power of the number of times that we failed. And so this is kind of thinking about our rules with independent events for probabilities. And that was kind of like when we looked at saying, you know, what's the probability that two people own a dog? Well, we took probability that person one owned a dog times probability person two owned a dog. So now we could say, okay, well, what's the probability that we selected 3 people and 2 of them owned a dog? That'd be the probability person one owns a dog times probability person two owns a dog times probability person 3 did not own a dog. But there's different arrangements that you can have for that, which is where our combinations come into play. Now, if you're trying to find the mean of a binomial distribution, you simply can do n times p. Standard deviation, you can actually just do n times p times q and take the square root. Now, if we wanted to find the probability that x was less than or equal to little x, we'd have to do the probability that x equals 0 plus the probability x equals 1 plus all the way up to the probability x equals x. We only have a nice formula for saying the probability that x equals some number. So if we're looking for probability x is less than or equal to that, there's quite a few things that we have to find and then add them up. Now, our calculator can help us in this situation. So using the formula is not necessarily efficient, especially if we're trying to look for the probability of less than, more than, at least, less than or equal to, at most. And so oftentimes the calculator is going to save time with crunching these numbers. There's going to be 2 formulas that are useful on the calculator, the binomial PDF and the binomial CDF. On the TI-83 or 84 calculator, they're called binom PDF, binom CDF. We need to know how and when to use each of these to make life easier. And in case you're curious, this is what the notation will look like in your calculator. Depending on the age of your calculator, it may give you a menu for entering things. There's a chance that you will have to type each of these in one by one as well. Now, before we get to how to find these functions on our calculator, we want to make sure that we're able to rewrite it. So we have probability x equals x, or probability x is less than or equal to x. So we're going to go through and do a couple examples here to make sure that we can rewrite things so that we're ready to use our calculator. If we're looking for the probability of more than 3, that's the probability that x is greater than 3, which would be equal to 1 minus the probability that x is less than or equal to 3. Probability of at least 3. Probability of at least 3 would be the probability that x is greater than or equal to 3, which is 1 minus the probability x is less than 3, which is equal to 1 minus the probability x is less than or equal to 2. So what we're using here is we're using some complement rules. And in addition to using our complement rules, we're also keeping in mind that this is a discrete distribution. So being less than 3 is the same as being less than or equal to 2, because if you have to be smaller than 3 and you have to be a whole number, the biggest thing that you could be equal to is 2. Now, the probability of less than 3 would be equal to the probability of x is less than or equal to 2. Probability of at most 3 is probability x is less than or equal to 3. And then probability of exactly 3 is probability x equals 3. Now, in each of these, we are getting it to something where we have less than or equal to some number or equal to a number. And we're aiming for getting it to where we have this less than or equal to, because that is what our calculator wants us to have for when you're using the binomial CDF. We're only going to use the binomial PDF on this equals 1, and that's because it has equals. And I want you to think of that P as kind of standing for precisely. It equals precisely one number, and the CDF, C is more for like cumulative. So it's everything up until that number. Now, to find these in the calculator, you need to be in the distribution menu. So you're going to hit second and then vars, and that gets you to the distribution menu. Both binom PDF and binom CDF should be able to be found underneath this menu. And again, this is instructions for TI-83 and TI-84 calculators. So let's do an example. If a seed is planted, it has a 90% chance of growing into a healthy plant. If 9 seeds are planted, what is the probability that exactly 2 do not grow? Now, I have to be careful about the wording of this problem here. The wording is a little bit tricky. So we're given a percent chance of growing into a healthy plant, but we're looking at the probability of not growing into a healthy plant. So when we're thinking about our probability of success, it's not going to be the 90%. First off, we're going to change from percent into a decimal. And then secondly, this probability listed here is for growing. We're looking for the probability of not growing. And the probability of not growing is what we're kind of considering a success here, because we're trying to find plants that do not grow, or seeds that do not grow. So when we're looking at the binomial distribution, we're wanting to kind of think, okay, what is my N, what is my P, and what's the probability that I'm looking for? So here we have N 9 trials, P our probability of not growing, which is what we're considering our success, is going to be 0.10, and we're looking for exactly 2 do not grow. So we have our formula. We could plug it into our formula if we wanted to, or we could just use the calculator. Either way that you go about it, you should end up with P of x equals 2 is equal to about 0.172. Here's another example. A high school baseball player has a .286 batting average. In one game, we're going to assume that he gets 9 at-bats. What is the probability he will get at least 6 hits in this game? If he's getting 9 at bats, that would mean that our N is equal to 9 again. Our batting average is going to be our probability of success. And we are looking for at least 6. So at least 6 is x is greater than or equal to 6. So we have to go through and we have to change things around so that we have a less than or equal to symbol in there. So instead of saying the probability x is greater than or equal to 6, we'd say 1 minus the probability x is less than 6 using our complement rule there, because either you're greater than or equal to 6 or you're less than 6. And so that's how we're able to use the complement rule. And then instead of saying less than 6, we know that we're discrete. So we would be able to say x is less than or equal to 5. So we're going to do 1 minus the probability x is less than or equal to 5. So that means on our calculator, we are going to be doing 1 minus binom CDF, 9, 0.286 I can read here, and then 5. So plugging everything in. And we end up with the probability of at least 6 bats, at least 6 hits in the game would be 0.020. And this is one that was kind of a tricky one to round, so do make sure that you take note of what your calculator is showing you and how that does round to 0.020. One common mistake that students will make on these types of problems is incorrectly selecting PDF or CDF. So always make sure that you're selecting the correct one. Another example here, working with the binomial distribution. About 1% of the population has a particular genetic mutation. 200 people are randomly selected. Find the mean and standard deviation of the number of people with the genetic mutation in such groups of 200. So here we have 200 people. We are trying to find people that have a particular genetic mutation. Only 1% of the population has the genetic mutation. So it means the probability that we find somebody with the mutation when we're randomly asking people would be 0.01. Probability we do not find somebody with the mutation would be 0.99. And we're going to go around, we're going to ask 200 people, which means we're going to do 200 trials. So we have our summary here of n equals 200, p equals 0.01, and q equals 0.99. So then our mean, we're just multiplying n times p together. So our mean is going to be 2. And then our standard deviation is n times p times q, and take the square root. So our standard deviation would be about 1.4. So that's a little bit about the binomial distribution that gets us started here. We also want to talk about the other special distribution that I said we would discuss, which is the Poisson distribution. The Poisson random variables count the number of times that a certain event will occur over a specific interval. Some characteristics here: the probability that the event occurs in a given interval is the same for all intervals, and the events occur with known mean and independently of the time since the last event. Our probability for finding the formula for finding the probability that x equals little x is equal to e to the negative lambda times lambda raised to the x, all divided by x factorial, where y is the mean of the, where lambda is the mean of the event. So that upside down y is pronounced lambda. Now, we are able to do a lot of this on the calculator. It kind of works the same way that our binom did. So we need an equals or less than or equal to all of the time. And again, the equals is going to be a PDF. The less than or equal to is going to be a CDF. So on our calculator, just like with the binomial, we're going to have two useful functions. And as we're entering these into our calculator, we're always going to enter lambda and then x. Again, PDF is when we're precisely equal to a number. CDF is when we're looking for cumulative distribution. Again, we're finding these underneath the same menu that we were looking at before for the binom. So you're going to hit second and then vars. That's getting you into the distribution menu. Then you're going to look for Poisson. It should be toward the bottom of the list. So let's do an example. A certain kind of sheet metal has on average 9 defects per 12 square feet. Assuming a Poisson distribution, find the probability that a 19 square foot metal sheet has at least 10 defects. So here we have to figure out on average, how many defects do we have? So like how many defects are there per square foot, and then how many square feet are we looking at? So basically we're saying on how many do we expect to see in the sheet size that we are looking at. And if we're expecting to see 9 defects per 12 square feet, and then we're looking at a 19 square foot thing, we'd be doing 9 divided by 12, giving us the number of defects per square foot, and then taking that times 19. So we'd expect to see about 57 divided by 4 defects in a 19 square foot metal sheet. Now, we are looking to see what the probability is that there is at least 10 defects. So looking at that probability, we are saying the probability that x is greater than or equal to 10 is equal to 1 minus the probability x is less than 10, using that complement rule there. And then knowing that we are in a discrete distribution, we can go ahead and say that's equal to 1 minus the probability that x is less than or equal to 9. So at this point, you're able to type it into your calculator. So you're saying 1 minus Poisson CDF, your lambda value, and then your x value. And we should get that the probability that there are at least 10 defects is equal to 0.902. Now that wraps up chapter 4, and chapter 4 wraps up our first unit together.